All right, in this lesson, we're going to look at a really cool example of dropping a tennis ball and a basketball together, and we are going to consider placing the tennis ball directly on top of the basketball, directly on top, dropping them together, and then what we will see is that the tennis ball is going to acquire a lot of energy from the basketball and actually go way higher than we think it should. And as I said in the index for this video lecture, please go onto YouTube and search Physics Girl Tennis Ball Basketball Drop, and she has a very good video illustration of the dramatic effect that we are going to talk about here. Before we talk about the dramatic effect, let's talk about the not dramatic effect of dropping a basketball or a tennis ball from a height little h, as I have shown over here. So, and I have that kind of designated as the normal situation. So normally we start out with a potential energy, right? mgh. So when either the basketball or the tennis ball strike the ground, right? Their velocity that they have when they strike the ground is going to be the joule value of all of that mgh converted into kinetic energy, right? So if the collision with the ground is perfect, both of them would bounce back with a speed v, and in the world's most perfect collision, no air resistance, no energy removed, they would bounce back to the same height h. And we know, of course, in actuality, they will bounce back to a somewhat lower position based on the elasticity with the ground when they bounce. Okay, so what is going on then when we place the tennis ball on top of the basketball, drop them together, and they hit the ground? So this is where we are really going to pick up our analysis, and really, we're going to pick up our analysis just after this position Roman numeral 2, where we are saying the tennis ball, since it strikes first, has hit the ground perfectly, is bouncing up perfectly with a speed v, and the tennis ball, I've separated it in the picture, but the tennis ball, we're saying, still has its downward velocity v. So the trick to getting the analysis and ultimately the result correct is to know, I think, to start with this condition. Okay? Well, the rest of it, I think, falls into place pretty readily on what we already know about relative motion and objects leaving moving platforms, because when we look at the motion of the tennis ball with respect to the basketball, when we go from this to this, right? So here, this is the perspective with respect to the ground, right? So with respect to someone here on the ground, that's a bad person, but this person sees this. The tennis ball, with respect to the basketball, from the perspective of the basketball, has a speed of 2v. That's perfectly valid. We can do that. Now, in terms of conservation of momentum, we have to always do it from the inertial observer's perspective. So here I have a better drew it in previously, inertial observer. Now, we're going to assume the tennis ball bounces perfectly off of the basketball. So that's what I have here. So make sure you get this into your notes. Bounces off the basketball perfectly. So that's the 2v that it comes up with. But we can't ignore the fact that the basketball itself is moving with a speed v. So the tennis ball actually rebounds with a speed of 3v. So if you recall from our normal situation, let's go back up top just for a second, we said it should rebound with a speed v. But we have just shown that based on the fact that we are assuming it's a perfectly elastic collision for all collisions, the tennis ball with the ground, the basketball with the ground, the tennis ball with the basketball, every collision is elastic. And if we assume that the mass of the basketball is very, very big by comparison to the mass of the tennis ball, all of those approximations give us the result we are looking at here. And we can see then that now our rebound kinetic energy up is not 1/2 mv squared, but it is 1/2 m3v squared. And that will equal a new mg capital H, where little m is the tennis ball, so that we see the new H for the tennis ball is 9 times the height that it would have gone initially without it. So again, this is kind of a conceptual approach. It is not a rigorous mathematical approach. At the end of the notes, I have kind of as an appendix a more generalized, more rigorous analysis of a tennis ball M1 striking a basketball M2 and looking at all of the math, but the algebra gets extremely messy, which I don't even show all the algebra in the appendix. But you are certainly welcome. I encourage you to look at that last page, and we will look at it a little bit together in class as well.